All right, the purpose of this video is to transition from confidence intervals into hypothesis testing. So in other words, the purpose of this video is to introduce to you a new concept called hypothesis testing. Now, what have we done? Okay, let me pump the brakes a little bit. What I like to do when I teach something, especially when the concept is a little challenging, is to embed it in something that we already know how to do. And since we just kind of wrapped up confidence intervals, let's think about what I've presented above the line here. So if we have a claim that the population mean value is 14, what we may consider doing is going out, gathering a sample. I've just said, we have a sample of 20. We end up getting a resulting sample mean of 15.2 and a standard deviation for the sample of 3.9. Construct a 95% confidence interval. Well, that should be really easy to do now. We just go to, tstat one sample with summary and type in the mean of 15.2 and type in the sample standard deviation of 3.9. Our sample size is 20. Select the confidence level that's appropriate, which in this case is 95%, and calculate the confidence interval. Well, 13.4 up to 17.0 would be the 95% confidence interval. Let me try getting that a little clearer. Okay, so because 14 is contained in the interval, we would have no reason to refute the claim, or in other words, maybe reject the claim based on our confidence interval. Now, this approach works kind of, but we find out as we learn more and more about hypothesis testing and confidence intervals that oftentimes confidence intervals will give us different outcomes than hypothesis testing. So that's going to be the fun part, is wrapping our mind around all of that. But hypothesis testing is a statistical procedure that is used, I don't know how many times a day, but many, many, many times a day in research. So that's what I am going to attempt to teach you. Now, first of all, let's think about it, in general, what is a hypothesis? I think of a hypothesis in general as just being an educated guess. If I think about hypothesis in the context of statistics, I think about it as being a claim about a value in a population. This, I believe, would be a hypothesis. It's a claim, right? The mu value is 14. I've given you a couple of examples here. Let's say that someone makes a claim that they feel that 38% of people believe in ghosts. Well, that's a claim that could be a hypothesis. Another claim, maybe someone may say that Tim Hortons in Portsmouth, that the average wait time from 8 a.m. to 9 a.m. is 12 minutes. Again, that is a claim. What hypothesis testing does, it gives us a very rigid process or procedure for testing a claim about a population value. Now, to provide structure to our, let's see if I can get that clear. To provide structure to our test, our hypothesis test, we create these things called a null hypothesis and an alternative hypothesis. Now, this is one of these things that really needs to go in your notes in big old flashing neon lights. The null hypothesis, and that should be H sub O, is the claim. The alternative hypothesis, which is given as a statement H sub A, actually stands for what we want to test. So if someone makes a claim that 38% of people believe in ghosts, and we have reason to believe that less than 38% people believe in ghosts, so we'd like to test it, our null hypothesis will be H sub O, colon, P equal 0.38, because that's the claim, H sub A, P less than 0.38, because that's what we want to test. Let's say we believe that more than 38% of people believe in ghosts. H sub O, colon, P equal 0.38, because that's the claim. Yeah, redundant. H sub O, colon, P greater than 0.38, because that's what we believe and we want to test. Is the percentage of people who believe in ghosts just different than the claim? Maybe we're just in an argumentative mood and we don't care whether higher or lower. We just think it's different. H sub O, P equal 0.38, again, the claim. H sub O colon, I'm sorry, H sub A colon P not equal to 0.38, because that's what we want to test. Now, we're going to find out that these test of hypotheses are also appropriate for means. So we're going to look at means and proportions. And in an upcoming lesson, we'll look at these for slopes of intercepts. I'm sorry, slopes of regression models and intercepts. So we can also test claims statements about a population mean. So let's say that the claim that the average wait time at Tim Hortons, blah, 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 is 12 minutes. We'd like to test that the service is faster. So the claim, H sub O colon mu equal 12, because we're testing a mean, and H sub A colon mu less than 12, because that's what we want to test. If the average service is faster, then the average wait time will be lower. Let's say we feel on average that it takes longer, that Tim Hortons is slower than what the claim is. H sub O colon mu equal 12. Our alternative hypothesis will be mu greater than 12, because that's what we want to test. Now, the third situation, the third example, we'd just like to test that the wait time is not 12. We're not giving any direction of whether we think it's faster, slower, higher, below, whatever. We just think it's not 12. Well, our null hypothesis, as you would expect, our alternative hypothesis, probably by now, as you would expect. So the first key in conducting a test of hypothesis is to get the null and the alternative hypotheses set correctly. So the general form for a hypothesis is H sub 0, a colon, a parameter value for now. It's mu or p, because mu is the notation that we use for the population mean, and p is the notation that we use for the population proportion. Whatever goes here has to go here. If mu is here, mu has to go right there. If p is there, p has to go right there. Now, what we get over here is the claim value. What's the claim that we're testing? And then we get down to the same value must go there. If 104.7 is there, 104.7 has to go there. If 22.9 is there, 22.9 must go there. Another must is this must always be equal to. We never test a claim that something is equal to. This is the claim. This is the test. We make a claim that something is equal, and then we test that it's not equal. It's not equal because it could be less than. It's not equal because it could be greater than. It's not equal because it could be not equal to. Now, we get into things called one-tail versus two-tail test. And in a nutshell, if this is all determined by our null hypothesis. So in a nutshell, if the H sub A is less than or greater than, we have what's called a one-tail test. If the H sub A is not equal to, we have a two-tail test. Now, we have to get into ultimately a decision about the null hypothesis. I pump the brakes. Let me circle back to that. It's extremely, extremely important. What is the goal of a test of hypothesis? To make a decision about the claim, to make a decision about H sub O. we're either going to reject H sub O or we're going to fail to reject H sub O. If we have a greater than sign in the alternative hypothesis, then we put our rejection region greater than our claim, which will be in the center of our distribution. If we have a less than sign in our alternative hypothesis, then we go less than the center. So our rejection region is below, less than the claim, which again will reside right here. If we just have a two-tailed test not equal to, then we put some region down here and we put some region up here. And these are the fail to reject. I'm sorry, those are the reject. And this is the fail to reject region. All right, again, we're going to learn this in small chunks because there's a lot going on with hypothesis testing. So someone makes a claim that 52% of working professionals use LinkedIn. I use LinkedIn, not a lot, but I have an account. So we'd like to test that. So we, do what we do in statistics, right? We collect a random sample. Let's say we talk to 1,000 working professionals and we ask them if they use LinkedIn. Let's say 556 report that they use LinkedIn. So my p-hat, my sample information is 556 divided by 1,000 or 55.6%. Now, I want you to think about this. Is 55.6% far enough away from 52% for us to reject that claim? To reject the claim that is higher or that is just different? Well, you might say, well, I don't know, 55.6 is pretty close to 52, right? So, well, what about 60%? Would that be far enough away? It's still within 8%. This is a sample, and that's a claim about a population. We know the samples vary because of sampling variability. So it's possible that we could get a, 1,000 people, 600 people to say that, when this is still a statement about the population. What about 63%? What about 72%? What about 81%? What about, once we go up here, it's kind of obvious, right? But in other words, where is the line in the sand that tells us our sample data is too far from the claim for us to believe the claim? Where is the line in the sand? Well, guess what I'm going to teach you now? What is the line in the sand? Well, the line in the sand is created by things called critical values. And as we saw in confidence intervals, when we model proportions, we use z-criticals. When we model means, we use t-criticals. We use z-criticals for means if the population standard deviation is given, but that's very, very, very rare. And it all depends on something called an alpha and the number of tails, one tail or two tail. So connecting all this stuff, we have confidence intervals that we ran into last time. The three primary confidence intervals are 90%, 95%, and 99%. If we have a one-tailed test, the alpha is just the percentage from 1. We need these two numbers to add up directly to 100 or 1. 0.95 plus 0.05 is 1, so that's a one-tail alpha. 0.99 plus 0.01 gives me 1, so that's a one-tail alpha. When I have a two-tail, then I have to take the one-tail alpha, divide by 2, and put half of that alpha in one tail and half of it in the other. Half the alpha in one tail, half in the other, half one tail in one tail, and half in the other. So if I am testing, for example, H sub O p equal 0.14 against p greater than 0.14, and my alpha is 0.05, I'm going to put 5% of the area under the curve in the right tail, because greater than, for my rejection region. What if I'm testing H sub O, P equal 0.14, H sub A, P less than 0.14, my alpha is 0.01. Less than, I'm going to put my tail down to the left. My alpha is 0.01. I'm going to put 0.01 of the area to the left of this line. What if I have a two-tailed test, P equal 0.14 versus P not equal to 0.14, and I'm testing at 0.05 alpha? I'm going to put half of my alpha in one tail, half of my alpha in the other tail. Again, these two tails are what? They are our rejection regions. We're too far away from the claim to believe that the claim is true, so we're going to reject it. These fundamental basic ideas are so important in being able to carry out tests of hypotheses. So let's find the location of the test statistics. So the first thing we do for proportions after setting up the null and alternative hypotheses and stating alpha is we calculate what's called a test statistic. And the test statistic for portions is z equal p hat minus p divided by the square root of p times 1 minus p over n. This, of course, is the standard error. So what we're measuring here, we're measuring the difference between what we observe in the sample and what the claim is in the population in standard error units. So let's say the P, what we get from our sample is 156 out of 988. And let's say we're testing at a level 0.05. So alpha is 0.05. This value is often referred to as the level of significance of your test. Gang, I know I'm throwing a lot at you, but I'm doing the best I can. There's just a lot of stuff. If something doesn't make sense, rewind. This first video is critically important that you understand reasonably well what I'm trying to teach you. So if something doesn't make a lot of sense, rewind and listen to it again, okay? So I'm going to put p hat in there. If you put in your calculator 156 over 988, you'll get 0.1579. This is the claim, 0.14 from the previous page. And then I put p, 0.14, times 1 minus p. So 1 minus 0.14 is 0.86 divided by the total sample size of 988. When I get that, I get 1.62. All right. So if I'm testing P equal 0.14 versus P greater than 0.14, I have this line in the sand right here. And how do I come up with that Z, that line in the sand being Z equal 1.645? Well, I do it just exactly like I did before. I go to stat, I go to calculator, I go to normal, mean 0, standard deviation 1. I need the tail in the right area, so I need greater than. My alpha level is 0.05, so I need 0.05 up there. And I hit compute, and you'll see I get 1.645. If my test statistic is to the left of 1.645, I fail to reject. If my test statistic is greater than 1.645, let's say it had been 2.3. 2.3 is up here somewhere, right? Then I would have rejected H sub O. The only choices that you have are to reject or fail to reject. And if we fail to reject, which we did in this case, we're not saying that H sub O is true, that P is equal to 0.14. All we're saying is, based on our sample data, we cannot reject the claim that P is equal to 0.14. We still may not believe it. We still may want to test it again, but based on our sample data, we cannot reject that claim, that statement about P. Again, circling back to the way that I started out here, just an FYI, confidence intervals and hypothesis testing results do not always agree. I have seen, and I'll end up showing you an example where H sub O is maybe, whatever, and we're testing H sub O maybe mu greater than 12. I have seen many situations where the hypothesis test will reject H sub O, but our confidence interval will contain 12. Well, those two things are contradictory, right? Hypothesis testing rejecting 12, rejecting H sub O, says that mu greater than 12 is more believable. But our confidence interval contains 12, which says we should reject that. So again, hypothesis testing gives us more tools in our toolbox, and it is just a widely accepted statistical procedure that you need to learn, okay? Or at least I feel you need to learn. All right, that's it. Take care.